Mars should be silent. There's no rain, barely any air. So why did NASA record thunder there? Today, you'll hear a sound that shouldn't exist, and it changes everything we thought we knew about the planet's weather. On a dry world with no rain clouds and such a thin atmosphere, how is it possible to capture something like thunder? The answer came from a rather unorthodox idea that involved a microphone attached to a NASA rover. Today, you'll see how this team managed to identify electrical discharges and a tiny Martian thunderclap directly from the surface of the red planet. Before we get to the discharges, it's worth understanding the stage where any sound has to perform on Mars. The Martian atmosphere has something like 1% of Earth's surface pressure and is dominated by carbon dioxide. In practical terms, there are very few molecules available to vibrate and carry acoustic energy forward. The result? Sound waves spread with difficulty, lose intensity much faster, and travel much shorter distances. To make things worse, the extreme cold, with temperatures often below -60 degrees Celsius, reduces the energy of the air particles, leaving everything even more still. In this scenario, the speed of sound drops to about 240 meters per second, well below the roughly 340 meters per second we measure here. The combined effect of this rarefaction with the cold not only lowers the speed, it also changes how sounds dissipate, making everything more muffled and less defined to our ears. There's also a curious detail that affects how sound is experienced there. On Mars, different frequencies propagate in different ways. Higher-pitched tones die out quickly, almost as if they're swallowed by the atmosphere. Lower frequencies can travel a bit farther, but nothing dramatic. The result is an acoustic landscape that's strange by earthly standards, where the world seems to speak quietly all the time, even when something actually happens. Perseverance, the mission that landed in 2021, carried working microphones to the surface and brought the first practical verification of this behavior. It recorded the sigh of the winds, the noise of the wheels crossing the ground, and even the sound of laser pulses used to vaporize tiny bits of rock during chemical analysis. Putting these pieces together, the impression is that Mars sounds like a huge acoustic chamber in which sound exists but is quickly smothered by environmental conditions. In other words, the planet is quiet not because nothing happens, but because its atmosphere prevents sonic events from spreading with vigor. With that backdrop, the detection of electrical discharges takes on huge significance. NASA announced that it managed to confirm a crackle of lightning on Mars based on recordings from the rover itself. Think of that snap you hear when you switch on an electric stove igniter. It's that kind of sound, only arising in a completely alien context. This discovery answers a question that had hovered over the scientific community for decades. Do Martian dust storms generate electricity like terrestrial storms do? We now know they do. And not by indirect inference, but by direct audio record combined with electromagnetic data captured by the instrument. Perseverance, equipped with the SuperCam microphone, spent a long stretch collecting sound samples and environmental signals. In a carefully analyzed 28-hour slice of audio, researchers identified 55 occurrences consistent with electrical discharges. Among them, 7 episodes were recorded from end to end, with every acoustic and electronic stage of a complete lightning event, from the first snap to a tiny peal of thunder. Almost all of these events showed up in rougher weather, during dust storms or when the rover crossed paths with dust devils, which are extremely common in the Martian landscape. The sound you're about to hear is the real capture of a mini Martian thunderclap. What triggers this electrical behavior? The explanation lies in friction between moving dust particles. When they rub and collide, they build up charges that eventually need to discharge. But dust alone isn't enough. That's where the wind comes in. Of the 55 detected events, 54 occurred during the strongest gust periods measured by Perseverance, especially as storm fronts passed. In other words, the wind boosts contact between grains, intensifies electrification, and creates the ideal setup for discharges. On top of that, 16 of those discharges appeared when the rover encountered dust devils. Until then, these whirlwinds had been studied through images and thermal signatures. Now, they also reveal their electrical side, indicating they're more energy-rich phenomena than previously thought. The 7 complete records made it possible to identify a very specific signature, almost like a fingerprint. First, there's a sudden electronic snap caused by interference from the discharge in the microphone's circuitry. Next comes a short decay lasting around 8 milliseconds. Right after that appears a component that surprised even the skeptics, a small thunderclap, the result of rapid expansion of air heated along the discharge's path. It's the same physical mechanism that produces thunder on Earth, but reduced to a scale consistent with a cold, rarefied environment. On Mars, the heat generated by the discharge can still dilate the gas around it, producing a pressure wave. It spreads for only a short time and distance, but it's enough to leave its acoustic mark. To make sure this pattern wasn't just random noise, the team replicated the process in the lab. They created controlled mini-electrical discharges and recorded at the same time their electromagnetic signature and their sound. The comparison between what happened in the lab and what the rover picked up on Mars lined up convincingly. This cross-check strengthens the interpretation that we were indeed hearing Martian electrical discharges and their tiny associated thunder. Among the study's several new findings, this experimental validation is a key point because it rules out alternative hypotheses and gives confidence to extrapolate what was observed to other Martian scenarios. Of course, the energy involved in these Martian lightning events is extremely small when set beside a typical Earth lightning bolt. Most of the recorded events ranged between 0.1 and 150 millijoules, values that are almost negligible compared with a terrestrial storm. For reference, a common lightning strike here can release on the order of 1 billion joules. We're talking orders of magnitude apart. Even so, it's precisely this modest scale that makes the discovery elegant. Weak as they are, the discharges leave a detectable signature that matches what physical models predict for a cold, thin atmosphere. That opens an investigative path that goes far beyond mere curiosity. From an engineering standpoint, knowing these small discharges exist helps design future probes, instruments, and habitats with proper protection against interference and surges, however minor. Scientifically, the presence of atmospheric electricity enables exploration of discharge-induced chemical reactions, which is useful for thinking about the atmosphere's evolution and the transformation of compounds at the surface. Depending on conditions, this kind of energy can act as a trigger for processes that unfold slowly on Mars, influencing everything from soil chemistry to how dust and ice interact over the seasons. There's also a fascinating, more speculative yet fully relevant angle. Some scenarios that discuss the origin of life on Earth include electrical discharges as an energy source for fundamental reactions, especially in environments rich in certain gases. We're not saying Mars had or has the same conditions, but the simple fact that the planet produces discharges, however tiny, fuels new tests and simulations. If at some point in Mars's past there was a thicker atmosphere, with more water vapor and more active chemistry, the discharges could have played roles different from what we see today. Probing that past with the help of electrical clues is a concrete possibility that gains momentum from these records. In light of all this, the idea of thunder on Mars stops sounding absurd and becomes a piece that's completely consistent with local physics. It's a discrete, fleeting, short-range thunderclap, born of a tiny discharge in very thin, cold air. But it is, nonetheless, thunder. It confirms that electricity is part of Mars's climate repertoire and paves the way for missions that use microphones and dedicated sensors to map this behavior in different regions and seasons of the year. From the initial crackle to the small pressure wave that spreads out, we now have an acoustic portrait of a phenomenon that, until not long ago, was only a hypothesis. If you enjoy following breakthroughs like this, mixing cutting-edge science with discoveries that reshape our view of neighboring planets, this is the perfect time to support the channel. Leave a like because it really helps the video reach more people. And if you're not part of it yet, subscribe now so you don't miss the next chapters of this exploration. Mars keeps surprising us, and with each new data point we get a bit closer to understanding not just the red planet, but the very history of our solar system. Thanks for watching, and see you in the next video.